welcome to another module in this massive open online course on estimation for wireless communication systems, and we are looking at OFDM, that is orthogonal frequency division multiplexing, and we said that OFDM very efficiently overcomes the inter-symbol interference in a wireless channel. Alright, so we are looking at basically OFDM, which is your orthogonal frequency division multiplexing, and we are considering, as an example, we are considering a system with n equal to 4 subcarriers, and we said that x0, x1, x2, x3, these are the n equal to 4 symbols loaded onto the subcarriers. These are basically your n equal to 4 symbols loaded, which are basically loaded onto the subcarriers, basically, which means that we are looking at the n equal to 4 point IFFT, yeah, the inverse fast Fourier transform of these to generate the sample. So, we are loading capital X0, capital X1, capital X2, capital X3 onto the subcarriers, which is we are taking the n point or 4 point IFFT to generate the samples, and the samples are basically your X0, X1, X2, X3, where your kth sample, these are the samples in time domain which are actually transmitted over the channel, and therefore, basically your kth sample xk equals sum L equal to 0 to n minus 1 xl e power 1 over n, since this is an IFFT, e power j 2 pi k L divided by n. Now, substituting n equal to 4, I have L equal to 0 to n minus 1, that is 3, xl e power j 2 pi k L by 4, which means your sample xk equals 1 over 4 summation L equal to 0 to 3 xl e power j pi by 2 k L. So, this is the kth sample which is generated by the IFFT. So, the kth sample generated by the IFFT, correct. And now, we are not simply transmitting the samples, we are adding a cyclic prefix, that is, we are taking some samples from the tail of the block and prefixing them at the head of the block, and this is known as the cyclic prefix. Precisely in this example, we have taken one sample, but one can take more also, alright, and that depends on the length or the number of taps in the channel response. Okay. So, basically what we are doing is we have x0, x1, x2, x3, and what I am doing is basically now I take x3 and prefix this, and this is termed as your cyclic prefix or CP, or basically the CP. And now, when you take this block with cyclic prefix, this is your block of samples. So, the OFDM transmission takes place in blocks. So, this is the block of samples with your cyclic prefix and you transmit this across the ISI channel. Transmit this across the channel with intersymbol interference, and what is the channel? We are considering a 2 tap intersymbol interference channel, that is yk equals h0 xk plus h1 xk minus 1 plus vk. This is the 2 tap, this is your basically L equal to 2 tap ISI channel. This is your L equal to 2 tap ISI channel, and now when you transmit the samples with the cyclic prefix, that is the cyclic prefix block of samples across this ISI channel, what you get is that the channel action becomes a circular convolution. So, the output basically y is the circular convolution of the channel with the transmitted samples plus the noise, and that is what we have also seen yesterday, that is also what we have seen in the previous modules, that is y equals h times x h, and where this is basically your circular convolution in the time domain, that is in the domain of the circular convolution, and it is important to remember that this is the circular convolution in the time domain for the samples. Okay, this is the circular convolution in the time domain, that is the time domain for the sample. So, there is still inter-sample interference, that is the inter-sample interference is still there, that has not been removed. However, now once you take the FFT and convert it into the frequency domain, now you take this whole system, you take the fast Fourier transform FFT, or basically which is the same thing as your DFT, and convert it into the frequency domain. And once you convert it into the frequency domain, what you have is that the circular convolution becomes a multiplication, that is FFT of h times the FFT of x plus the FFT of your noise. Let me write this multiplication explicitly. So, in the FFT domain, this becomes a multiplication in FFT domain, or basically your frequency domain. Let us call this, rather than FFT domain, probably a better word for this is the frequency or subcarrier domain. Remember, in the frequency we are talking about the various subcarriers in the frequency domain. So, in the frequency domain it is a multiplication, which means now basically if you look at the lth subcarrier, that is I have YL, that is in the frequency domain across lth subcarrier, is the product HL times XL, which is a symbol transmitted across the lth subcarrier, plus VL, where YL is the output symbol. Remember, this we said is the output, this is your output symbol across lth subcarrier. This is your channel coefficient for the lth subcarrier. Okay. This is the symbol loaded onto the lth subcarrier. This is something that we already see in the capital L. This is the symbol loaded onto the lth. This is the symbol loaded onto the lth subcarrier, and VL is basically the noise on, this is your noise on the lth subcarrier. This is the noise on the lth subcarrier. So, this is the model, and therefore, what you are saying on the subcarrier, on each subcarrier there is no, and this is important to observe, that on each subcarrier there is no ISI. That is, there is no intersymbol interference on each subcarrier, because YL equals the coefficient HL times the symbol XL on the subcarrier plus VL. So, basically there is no interference, intersymbol interference on the symbol XL, capital XL, which is basically the symbol loaded onto the subcarrier. Therefore, it very efficiently removes ISI using simply the IFFT at the transmitter and the FFT operation at the receiver. And now, since we have n equal to 4 subcarriers, let me simply explicitly write it down, so that we can formulate the system model and then see how the estimation of these channel coefficients can be done, and that is indeed going to be very simple. So, if I write the system for the n equal to 4 subcarriers, so remember we said we have n equal to 4 subcarriers corresponding to L equal to 0, 1, 2, 3, which means across subcarrier 0 I have y0 equals x0 h0, just writing hx as xh plus b0 because this is convenient, y1 equals x1 h1 plus v1. By the same token, again this is very simple, something that you can already guess, y2 equals x2 h2 plus v2, and y3 equals x3 h3 plus v3. This is across your n equal to 4. This is across your n equal to 4, this is across your n equal to 4 subcarriers, and now I can write this as a matrix. So, basically what I can do now is I can basically make a vector out of this. I can use it, I can model it, I can represent it using vector notation. That is what we have done many times before, and it is going to be very simple. Now, if I write it as a vector, now you can clearly see, let us say I write this as a vector, that is I have y0, y1, y2, y3, let me call this vector y bar. You can see this is basically this diagonal matrix of x0, x1, x2, x3, this is basically, let us call this matrix X, which is your diagonal matrix times the matrix of channel coefficients H0, or the vector of channel coefficients across each subcarrier, rather H2, H3 plus again the noise vector, that is the noise across each subcarrier, capital V0, capital V1, capital V2, capital V3. So, this is your channel vector, this is your noise vector, and remember this whole model is basically in the frequency domain. Because we are writing it across each subcarrier, this whole model represents the frequency domain representation of this OFDM system, that is YL equals XL, the symbol loaded onto the subcarrier L, times HL, the channel coefficient across subcarrier L, plus capital VL, which is the noise sample on subcarrier L. Okay. And now we have converted it into this matrix model where Y bar equals X times H bar plus V bar, where X equals, you can see this is an n cross n, that is in this case 4 cross 4 diagonal matrix. Y bar, this is an n cross 1 vector. H bar is your n cross 1, that is again 4 cross 1 coefficient vector, and V bar is basically your n cross 1 or basically your 4 cross 1 noise vector. This is your equivalent channel vector. You can think of this as basically your channel vector in the frequency domain, and you can think of this as the pilot matrix in the subcarrier domain, that is the diagonal matrix X. If you are transmitting pilot symbols onto the subcarriers, so this is the pilot matrix in the subcarrier domain, that is where and this is the received pilot outputs in the subcarrier domain. For channel estimation, these are the pilot outputs in the subcarrier domain. Basically what we are saying is, we are considering capital X0, capital X1, capital X2, capital X3 to be the n pilots loaded onto the n subcarriers. So basically what we are saying is, we have, for purposes of channel estimation, if we load the pilots onto the subcarriers, so these are your pilots loaded onto the subcarriers. These are the pilots which are loaded onto the subcarriers, and therefore what I have is, now I have your familiar Y equals X H bar plus V bar, where this is the pilot matrix. This is something that we have seen many times before, even in the downlink channel estimation, where we have the received vector basically Y equals pilot matrix X times the channel vector H plus the noise vector. And therefore now one can formulate the channel estimation problem, that is estimation of the coefficient vector capital H bar, as a least squares problem. So naturally I can now formulate this as a least squares problem, and it is going to be a very simple least squares problem. So channel estimation, I am going to formulate this as a least squares problem. This is going to be your least squares, that is LS problem for channel estimation, which is simply now, like many times before, Y minus H X bar square, and we would like to minimize it with respect to H bar, that is we would like to find the H bar which minimizes this least squares cost function, and that gives us the maximum likelihood estimate. Remember, that is also something that we had derived, and the least square solution again is very simple, that is H hat equals X Hermitian, considering complex symbols, X Hermitian, that is simply replacing the transpose by Hermitian, X Hermitian X inverse X Hermitian Y, that is basically, remember previously we had X transpose X inverse X transpose Y. I am simply replacing the transpose by Hermitian because of, to allow complex matrix X, yeah. And therefore what we have, and now therefore now let me write this again a little bit clearly, X Hermitian X inverse X Hermitian Y, this is the least squares estimate of the coefficient vector this is the least squares or the LS estimate of the coefficient vector, right, x Hermitian x inverse x Hermitian y, right, where y basically vector y is the FFT of the outputs received or the samples, output samples received in the time domain. Basically y bar is the vector of outputs across the various subcarriers, correct, and x is basically the diagonal matrix consisting of the pilot symbols which are loaded onto the subcarriers. And now if you observe something interesting, this x, this matrix x is a diagonal matrix which is basically invertible, right. So if you look at this, this is slightly different from the least squares that we have seen before. Your x is a x basically equals, in fact let me just write it explicitly, this is your x0, x1, x2, x3, which is, and only diagonal entries are non-zero, rest of the entries are 0. So basically your x is a diagonal matrix x is a diagonal matrix which is invertible, and therefore what you have, so this matrix is basically, this is an invertible matrix this is basically an invertible matrix, which means now what you have is normally, see remember previously we said, so this is an n cross n matrix. So x is basically a square, in fact diagonal matrix, hence x is invertible. Previously when we considered the pilot matrix, remember the pilot matrix we said is n cross m, where n is the number of pilot vectors and m is basically the number of antennas at the base station. That was in the case of multi antenna downlink channel estimation. Here we have something very interesting because of the nature of OFDM channel estimation. We have the pilot matrix x is n cross n, it is a square matrix. So therefore in fact it is invertible, and hence in this scenario particularly x Hermitian x, since x is an invertible matrix, this is not always true. So this becomes x inverse times x Hermitian inverse. This is only for this scenario because x is invertible. This is not because x is invertible. This is not generally true. This is only true in this scenario, because in OFDM, in this OFDM scenario, x is n cross n, it is an n cross n invertible matrix, and therefore now if I substitute this, I have h hat equals x Hermitian x inverse x Hermitian y bar, which is basically now x inverse into x Hermitian inverse into x Hermitian into y bar. Of course, you can see x Hermitian inverse into x Hermitian, this is identity. So this is simply now very interestingly simply x inverse y bar, where x is basically your, where x is basically, this x is basically your pilot matrix. Pilot matrix. And also since the pilot matrix is diagonal, since it is the diagonal matrix, x inverse is also very easy to compute. It is basically the inverse of each of the diagonal elements, that is the reciprocal of each of the diagonal elements. Therefore, x inverse is simply, since x is a diagonal matrix, this is also important to note, since x is diagonal, x inverse is easy to compute. When I say easy, it means it is efficient. X inverse is simply basically your 1 over x0, 1 over x1, 1 over x2, the rest are zeros. this is your diagonal matrix, and therefore, now if I look at h hat, the estimate of the vector h hat, that is estimate of h hat 0, h hat 1, h hat 2, h hat 3, this is simply x inverse, that is 1 over x 0, 1 over x 1, 1 over x 2, 1 over x 3, zeros, times the symbol vector received across the subcarriers, that is y bar, which is y 0, y 1, y 2, y 3, and now therefore, now since this is diagonal matrix, now if you look at this, you have 1 over x 0 multiplying y 0, you have 1 over x 1 multiplying y 1, you have 1 over x 2 multiplying y 2, you have 1 over x 3 multiplying y 3. So, therefore, the channel estimates are very simple, it is simply h hat 0 equals y 0 divided by x 0, h hat 1 is basically your y 1 divided by x 1, h hat 2 equals y 2 divided by x 2, and finally, h hat 3 equals y 3 divided by x 3. That is basically the estimate of the channel coefficient across each subcarrier L is simply the pilot output across the subcarrier divided by the pilot input across the subcarrier, and that is very simple to see. So, basically summarizing this channel estimate, the h hat k equals y k divided by x k. This is what? This is the estimate of coefficient, or let us write it in terms of L, since that is the notation that we are using, h hat L equals y L divided estimate of coefficient across subcarrier L. Y L is symbol across subcarrier L, the pilot output symbol, pilot output across subcarrier L, and XL is basically your pilot symbol this is basically the pilot symbol across subcarrier L, and therefore, if you look at this across each subcarrier, we have y hat h hat L is, it is very simple, the estimate of coefficient across subcarrier L is simply y L divided by XL, where XL is the pilot symbol loaded onto the Lth subcarrier, alright. So, the estimate h hat 0 is equal to, you can clearly see this is y 0 divided by x 0, h hat 1 equals y 1 divided by x 1, h hat 2 similarly equals y 2 divided by x 2, and h hat 3 this is equal to y 3 divided by x 3. And in general, therefore, one can say the estimate of the coefficient on the Lth subcarrier h hat L equals y L divided by x L. This is what is h hat L. H hat L is basically, this is the estimate of the coefficient on the Lth subcarrier. This is the estimate. This is the estimate of the coefficient on the lth subcarrier. All right. So, we are saying H hat L equals YL, that is the received pilot symbol, YL on the lth subcarrier divided by XL, which is the transmitted pilot symbol on the lth subcarrier. Okay. And therefore, now if I look at this, now if I look at the coefficients H hat 0, H hat 1. Now, remember what we said earlier, remember the H hat, the capital H's, what are they? They are the given by the FFT of the channel taps. Remember, we had H1, H0, H1 0 padded, and you look at the n equal to 4 point IFFT or n equal to 4 point FFT or basically your DFT, you get the capital H's, which are the basically the channel coefficients corresponding to the subcarriers, right. These are the coefficients for the subcarriers. So, what are these? These are your channel taps, and these are the coefficients corresponding to the various coefficients of the subcarriers. So, the coefficients of the subcarriers, channel coefficients of the subcarriers are given by the 0 padded FFT of the channel taps. Now, therefore, from the estimates of the coefficients of the subcarriers, if you want to construct the channel taps, we have to look at the IFFT, right, because the channel taps FFT gives the channel coefficients on the subcarriers, the coefficients on the subcarriers, if you take the IFFT or the IDFT, you get back the channel taps. So, now we have the estimates of the channel coefficients on the subcarriers. How do we find the channel taps? Estimates of the channel taps, we take the IFFT or the IDFT, and therefore, naturally what we want to do is I have H hat of 0, H hat of 1, H hat of 2, H hat of 3, and what do? I basically take the IFFT or basically IDFT n equal to 4 point to get back your H hat 0, to get back the estimates of the, what are these? These are basically your estimates of the channel tap. So, these are the estimates of the coefficient, these are estimates of the subcarrier coefficients . These are, what are these? These are estimates of your channel taps. In other words, basically what we are saying is this H hat k, which is the estimate of the channel tap on subcarrier k on or the estimate of the kth channel taps is given by the n point IFFT, that is 1 over n L equal to 0 to n minus 1 H hat of L e raised to j 2 pi k L by n, and now here I am going to substitute n equal to 4. Now, substitute n is equal to 4, which means what I have is H hat of k equals 1 over 4 L equal to 0 to 3 H hat of L e power j 2 pi k L divided by 4, which is basically 1 over 4 L equal to 0 to 3 h hat of L e power j pi by 2 k times L. This is the expression for the estimate of the kth. This is the estimate for the expression of the kth channel tap. So, this is the estimate of the kth channel tap. Expression for the estimate of the kth channel tap, which is given by the IFFT of the estimates of the subcarrier coefficients, that is estimates of the channel coefficients of the various subcarriers, and the size of the IFFT is, or the IDFT is n equal to 4 point. Okay. For example, h hat of 0, if you look at h hat of 0, all I have to do is I have to substitute basically your k equal to 0 corresponds to k equal to 0. So, this is 1 over 4 summation L equal to 0 to 3 h hat of L e power j pi by 2 k equal to 0, 0 times L. So, this quantity is 1. So, this is basically 1 over 4 summation L equal to 0 to 3 h hat of L e power, well, this whole thing is 1. So, it is simply summation 1 over 4 L equal to 0 to 3 h hat of L, and h hat of 1, which is the estimate of the first channel tap, is 1 over 4. Basically, that corresponds to k equal to 1 L equal to 0 to 3 h hat of L e power j pi by 2 k equal to 1 into and L. So, this is basically 1 over 4 L equal to 0 h hat of L e power j pi by 2 into L. So, this is estimate of channel tap 0 or estimate of 0th tap, and this is basically your estimate of the first tap. This is basically the estimate of the first tap. This estimate of the channel tap 1. Okay. So, basically what we have over here now, what we have done, we have comprehensively demonstrated how to do channel estimation for an OFDM system, that is orthogonal frequency division multiplexing system. So, in this module and the past modules, what we have seen is first we have formulated, we have developed the model for OFDM or orthogonal frequency division multiplexing based transmission, where we said we have symbols which are loaded into the subcarriers, that is basically you perform the IDFT followed by the cyclic prefix, transmit them over the frequency select or the intersymbol interference channel, right. At the receiver perform the FFT, that converts, that basically because of the cyclic prefix the action of the channel is that of circular convolution. So, basically in the FFT domain the action of the channel is that of multiplication, the channel coefficient is multiplied across each subcarrier with the transmitted symbol, plus of course you have additive noise at the receiver. And then we formulated, considering these symbols loaded on the subcarriers to be pilot symbols, we formulated the least squares channel estimation problem. We estimated the channel coefficients corresponding to the various subcarriers. In fact, we said that it's very simple. What you have to do is you have to take the received pilot symbol capital YL across subcarrier L divided by the transmitted pilot symbol capital XL on the Lth subcarrier, that is capital YL divided by capital XL, that gives capital H hat L, the estimate of the channel coefficient across subcarrier L. Remember, this is the channel coefficient in the frequency domain. Now, to get the time domain channel coefficients, what you have to do is you have to take the IFFT, similarly the n equal to 4 point IFFT, and then you get the corresponding estimates of the channel taps in the time domain. And so, that is how in brief or in summary how OFDM channel estimation works, alright. So, we will stop this module here. In the subsequent module, we will look at a simple example, because examples illustrate things clearly. So, we will look at an elaborate example to see how this whole mechanism of OFDM channel estimation works, alright. So, we will stop this module here. Thank you very much. you.